All right, so I wanted to do this lecture about circular motion here. So I'm going to kind of briefly go over circular motion. So these are the last two sections in Chapter 4 of Survey. So by the end of this lecture, I'm hoping that you are familiar with the following things. Some new terms, period, frequency, angular frequency, or I should probably call this angular velocity or angular speed, which that's what's used in the textbook, angular speed. So those mean the same thing. And then we're going to talk about objects in what is called uniform circular motion. That's objects moving at a constant speed. And then the trickier one is non-uniform circular motion. So that's objects moving in a circle, but speeding up or slowing down at the same time. And this last one is the trickiest one. That's where you have two kinds of acceleration. You have something called centripetal acceleration and tangential acceleration. So we'll be going through all of these things in this lecture. Okay, so we're going to focus now on an object traveling in a circle. This picture shown here is like the overhead view of a car. So imagine you're in the parking lot turning donuts in your car and you're making a circular path, and this is what it looks like from above. So the radius of that circle is r, and the velocity of your car is v, and you're traveling in a circle there. Remember, when we talked about two-dimensional kinematics, that dashed line there is the line that's traced out by the path of the object, and the velocity, the instantaneous velocity, is always tangent to that curve. So no matter where I am on this curve, if the car later is here, it would have a velocity pointing this way. And if the car later is here, it would have a velocity pointing this way. So the velocity is always, the direction of the velocity is always tangent to that circle. And that's actually, even if it wasn't traveling in a circle, it would be tangent to the curve. So the radius vector goes from the center of the circle to where the object is. The velocity is tangent to the circle. And hopefully it's not too hard to see that those two things are therefore perpendicular. So the radius r, the vector which goes from the center to the position of the object, and the velocity v are perpendicular to each other. There's 90 degrees between those two. So now I want to focus on the special case of what's called uniform circular motion. So not just any circular motion, but uniform circular motion. Uniform means a constant speed. So the object is traveling in a perfect circle at a constant speed. So you got your car on cruise control, hopefully not going too fast, in the parking lot, donuts, right? So the constant speed v. Now some terminology here. The time it takes for one time around the circle is what we call the period. Okay, so the period of the motion, that's how long it takes to go around the circle once. And of course the units of period are seconds. And the symbol that we use is t for some reason. Don't ask me why. It's always we use t. Just be a little careful because we've used t for other things like tension and also temperature, which we haven't covered. But so you have to know by context which t you're talking about here. You can't just like plug numbers blindly into formulas without knowing something about what the formulas mean. One other thing that's important to notice is that, tension is a force which has a vector on top of it. This is just a number, it's a time, so there's no vector. So that's one other way you can keep those things apart. Okay, now we talked about the average velocity. That's the displacement divided by the time. So over one revolution, your average velocity is going to be 0, right? So if you start the circle at one point, you go around the whole way around, your displacement is 0, so your average velocity is 0. Your average speed is not 0. Your average speed your speed never changes. It's equal to this v, but the direction of your velocity is constantly changing, so your average velocity is 0. Your average speed is the distance traveled divided by the time, but the speed doesn't change, so that means that your average speed is going to be the same as your instantaneous speed, so your speed never changes. What's your average speed if you go around the whole one circle? It's the distance traveled divided by the time. The distance traveled is the circumference of the circle. So let's say you start here and then you go all the way around once and come back to where you started. the distance you've traveled is 2 pi r, and the time that took is called t, the period. So the speed, or your average speed, all the way around, is the distance divided by the time, 2 pi r divided by t. But because your speed never changes, that means your average speed is equal to your instantaneous speed. And so this is a relationship at the bottom here, is a relationship between the velocity, the radius, and the time that it takes to go around. There are a couple other variables that you need to be familiar with when we're talking about uniform circular motion. So we talked about the period, that's the time it takes to go around once. There's also the frequency, f. So that's like, it's related to the period, but it's just 1 over the period. So the frequency is 1 over the period. So those two things are kind of telling you the same thing, it's just one is the reciprocal of the other. So f is frequency, it's like the rotation rate. In words, it's like how many rotations per second. So for example, if t is 10 seconds, that means it takes 10 seconds to go around once, then your frequency is 1 over 10. In other words, you've traveled 1/10 of the way around per second. Okay. The units of f are 1 over seconds, of course, and that has a special name, which is hertz. So the units of frequency are called hertz, and it's 1 hertz is 1 second, 1 over seconds. Okay. There's also a similar quantity called angular speed, which is given by the Greek letter, or denoted by the Greek letter omega, and it's very simply related to f just by a factor of 2 pi. Okay. So omega is 2 pi f. So all of these things, t, f, and omega, are all kind of telling you about, the motion there, but they're all related very simply, just with f is 1 over t, omega is 2 pi f. The units of omega are radians per second, so the interpretation of this is telling you what the angle is. What angle are you traversing in radians per second? So for example, if your angular speed is 2 pi radians per second, that means you've gone around the circle once in 1 second. Okay. So 2 pi is telling you how many radians do you travel through in 1 second. Remember, in case you don't remember the conversion between radians and degrees, there's 180 degrees in pi radians. So typically we use radians when we're talking about circular motion. You can combine all these things together. So on the previous slide I had v equals 2 pi r over t. That was the distance around once divided by the time around once. So 2 pi r over t. Now I could replace t as 1 over f. So I can get my velocity as 2 pi r f. And then the last thing I can do is take the 2 pi and the f, 2 pi and f. Those things all together are equal to omega. So I get v is equal to r times omega. This is actually a useful formula that we will come back to. V is equal to r times omega. So all of these things are kind of, there's not much here other than this here, that the speed is the total distance divided by the time. And then all we've done here is define two new variables, f and omega, and just related those things. So here's a clicker question, a very simple question. A car is going around a curve at a constant speed, as shown there. You can see that curve is mostly circular. And let's say it's traveling at a constant speed of 60 kilometers per hour. Between the two times shown, so initial time and final time, simple question for you, is the car's acceleration 0 or is it not 0? So go ahead and pause the video, see if you can wager a guess about this question. So hopefully you have committed to one of these answers by now. If you haven't, pause the video and make sure you have a guess. Okay. So the key point here is that acceleration is the change in velocity divided by the change in time. Now, you might be worried that the car is traveling at a constant speed, so doesn't that mean that the velocity is not changing? That's not right. Remember, velocity is a vector, so even though velocity is a vector, so it has a magnitude and a direction. The magnitude of the velocity is not changing because the speed is staying the same, but the direction is clearly changing, right? So the direction of the velocity is changing, If the direction is changing, the vector is changing. And that means that the velocity is changing here, so you do have an acceleration. The answer is the car's acceleration 0? No, it has acceleration because the velocity changes. Okay, let's do a little bit of work here to describe, we're talking about circular motion, so I'm going to do a little bit of a toy example, which is not a perfect circle, but it kind of, if you look at it, it looks a little bit like a circle. It's an octagon. So let's say you're traveling around in this path, A, B, C, D, E, F, G, H, and then back to A. So you're traveling around this octagonal path here. And I'm going to write 2 points on this curve here. So I'm going to call that point B and that point C. And suppose you want to know what's the direction of the acceleration, the average acceleration between points B and C. So let's think about that. The car is traveling at a constant speed, so let's go ahead and write 2 vectors. So this will be my, let's just call this VI, initial speed. And then at point C, it's got a different velocity, this way, VF. Okay. Just like that. And if I did it right, those 2 should be the same length. Now, remember, the average acceleration is the change in velocity divided by the change in time. Okay? And the direction of the acceleration is the same as the direction of the change in the velocity, the average acceleration. So let's try to line those vectors up. I'm going to put it like this. VI, if I did it right, will be something like that. VF is something like this. If I had drawn it, they should be exactly the same length. And what's the direction of delta V? Let me just label this. This will be VI. This will be VF. I need delta V is VF plus minus VI. So final minus initial. And hopefully it's not too hard to realize that the delta V is in this direction. You can see because VI plus delta V is equal to VF. Because VI tip to tail with delta V ends up at the tip of VF. And so that means that the direction of the acceleration here is pointing sort of down and to the right. And the question is, where should I draw this on the diagram? If it's the average direction of the acceleration between points B and C, well, where is the acceleration happening? It's happening right here. Okay? So if I were to draw that, it would be something like this. That would be the direction of the acceleration, A. Now, you could do this again with a bunch of other, I could do it again with point, let's say, E and F. So I invite you to try and do that. Write down the initial velocity at E, and then the velocity at F, and figure out the direction that points. And if you do that, you'll find that it points this way. And you'll find that no matter which way, no matter which point you choose, the direction of the acceleration at each of those vertices is always pointing towards the center of this thing. So every time the direction of the velocity changes, you have an acceleration, and that acceleration always points towards the center of this object. Now, this is not exactly circular motion, it's an octagon, but hopefully you can see how this is going to work when I do it with circular motion. If I just made a lot more sides, right, it gets closer and closer to a circle, and I would still have all of those acceleration vectors pointing towards the center. So there is an acceleration in circular motion because the direction of the velocity is constantly changing, and that acceleration always points towards the center of the circle. So we call this centripetal acceleration, not centrifugal, centripetal with a P, centripetal acceleration. Centripetal means center pointing, so it's pointing towards the center of the circle. So an object which is moving in a circle at a constant speed experiences centripetal acceleration. It points towards the center of the circle. The magnitude of that acceleration is v squared divided by r. V is the speed of the object squared divided by r. This second one is quite useful. Omega squared r, where did that come from? I used, let me write it here, AC is equal to v squared divided by r. And then I used, for v, there's a formula for v is equal to omega times r squared divided by r. That's omega squared r squared divided by r. And this cancels with this, and I get omega squared r. So that's where that second equality comes from. So that's the magnitude of the acceleration that the object feels, and it points towards the center of the circle that the object is traveling in. So maybe you want to know where that comes from, this formula for centripetal acceleration. You can get it from geometry. So imagine you've got some object here, which is traveling in a circular path, which is supposed to go looking like this, the green line, or the dashed line. And then at point A, it's at one point, and then later it's at point B. And you can see its velocity is always tangent to the circle, so there's some initial velocity and some final velocity there. Okay, let's say that the angle that is traced out by this circular path is called delta theta. So I'm just calling that angle delta theta. And if you want, you can make a right triangle here. So this, if I draw this here, I'm going to bisect that. This will be 90 degrees right there. So let me highlight this right triangle here. That's a right triangle. And I can do trigonometry on that triangle. The sine of the angle, which is this angle here, is delta theta over 2, is equal to the opposite, which is delta r over 2, divided by the hypotenuse, and the hypotenuse is this, right? Which is what I'm going to call r, the radius of the circle. Okay? So that's where this equation comes from. That's doing right trigonometry on that blue right triangle. Now, the claim is, if you take the velocity vectors and make them into a triangle, that the angle here is the same angle as this one down here. Can you understand that? So what is this angle here? Maybe it's better to think about this angle here first. This angle there, the green one, that's 90 degrees minus delta theta over 2, right? But we said before that these two are perpendicular, right? Let me see, different color. The velocity and the radius are perpendicular. So if this angle, the green one, is 90 degrees minus delta theta over 2, let me pick a different color. Let me make it red here. This one will also be delta theta divided by 2. Okay. So I can now draw another right triangle, which is this one. And this is 90 degrees. And this triangle, which I'm now highlighting in red, I can use trig on that triangle. Sine of delta theta over 2 is equal to the opposite divided by the hypotenuse. The opposite is delta v divided by 2, because I bisected it into two pieces. And the hypotenuse is the velocity vi. And really I'm using the magnitude here, so that's the magnitude of the radius vector r is the hypotenuse of the first triangle. The magnitude of the velocity v, or the speed, is the hypotenuse of the second triangle. Those angles are the same, so that means that this has to equal to this. Okay? So delta r divided by r is equal to delta v divided by v. So now I'm down here. Delta r, the distance traveled, is the velocity times the time. So I put in v delta t. And the change in velocity, that's the acceleration times the time. So a delta t. The delta t's cancel, and you get the acceleration is v squared divided by r. We call that centripetal acceleration. So this slide here is a derivation of the previous slide, explaining centripetal acceleration v squared over r. Where does that come from? You get it by doing some geometry here. That's basically it. All right, here's another clicker question for you. A car travels in a circle of radius r at a constant speed v. Sometime later, it's traveling in the circle with double the radius, but also traveling twice as fast. In which case is the magnitude of the acceleration larger? So the initial case, when r and v were smaller, but then I doubled both r and I doubled v. So is the acceleration bigger in the first case, or bigger after when I doubled them, or both the same? Go ahead and pause the video, see if you can wager a guess on this. So hopefully you have your answer now. Which case is it? The common mistake that students usually say when you're starting out is they think it's both the same. Because there's kind of this intuition that, well, if I doubled one thing and then I doubled the other thing, like nothing should change. But you have to be careful, because how does the formula depend on r and v? So remember that a, if it's traveling in a circle, is v squared divided by r. So if I double v, the v is squared. So if I double v, the whole thing goes up by a factor of 4. So this would be my a initial, would be vi squared over ri. My a final, if I double v, that's 2vi. I doubled it, and then I square it, divided by 2 times ri. And that becomes 4 times vi over 2 times ri. So you can see the denominator got bigger than the numerator got bigger than the denominator because of that square there. So the answer is that the acceleration will be bigger in the final case when r and v are bigger, because I doubled both, but the numerator got squared, so it went up by a factor of 4. Here's a quick example about centripetal acceleration. So you may not believe it, but you are experiencing centripetal acceleration right now. And that's because the Earth is rotating. The Earth is a sphere. It's rotating around its axis. So you are actually traveling in a circle as the Earth rotates around its axis. And not even that, but the Earth is also rotating around the Sun. So there's another circle in there. It's an ellipse, but it's close to a circle. And so you're also feeling a centripetal acceleration because of the Earth going around the Sun. So this is a simple question: which one is bigger, the acceleration from the Earth rotating on its axis, or from the Earth going around the Sun? So let's work this one out. I'm just going to write down the acceleration of each one. So I'm using here AC is v squared over r for each case. Now we don't know the velocity here, but we do know, hopefully, the period of each motion. So let's call the period of rotation of the Earth. So we do know how long it takes the Earth to go around. That's 24 hours. And we know that the amount of time that it takes the Earth to go around the Sun, how long is it? Hopefully you know. Call it the period of the orbit, that's 365 days. Okay. All right. Now, let's just try to figure out which is bigger, and the way I'm going to do that is to take a ratio. So I'm going to take the acceleration of the rotation divided by the acceleration due to the orbit, and that's going to be v squared of the rotation divided by r for the rotation divided by v squared for the orbit divided by r for the orbit. And if I simplify this a little bit, I get v rotation over v orbit squared times r orbit divided by r rotation, like that. So I'm just using the fact I divided by the fraction, so I multiply by the upside down or the reciprocal of that, and this is what I get. Now, I don't really know the velocity of the rotation. I mean, I could figure it out, but let's be a little bit faster about it. I'm going to use here v is equal to 2 pi r divided by the period, right? Because I know the period of each of those. So v is 2 pi r divided by the period for each one of those. So we're going to have here the acceleration, the ratio of these. So the top one is the rotation of the Earth, the bottom one is the orbit of the Earth around the Sun. I'm going to have on the top 2 pi r rotation divided by the period for the rotation, divided by 2 pi r for the orbit, divided by the period of the orbit. Whole thing squared times r orbit divided by r rotation. I'm doing this because I'm trying to show you how useful ratios are. I don't have to plug in a bunch of numbers. I just want to know which is bigger. And if I figure out this ratio is bigger than 1, then I know which one is bigger. Okay, so the ratios are quite useful in physics. Okay, simplify this a bit. There's a 2 pi on the top and a 2 pi on the bottom, so those cancel. And what have I got here? I've got r rotation over t rotation times t orbit divided by r orbit. So again, dividing by the fraction is multiplying by the reciprocal, r orbit over r rotation. Okay, now put everything together. I've got 2 of these, r rotation, because it's squared, on the top and 1 on the bottom. And then I've got 2 of the r orbits on the bottom and 1 on the top. So what do I have here? I'm going to have r rotation over r orbit. Only 1, because one of them cancels out because of this extra factor here. And then I've got 2 factors of the period, which are uncancelled. So I will have here t orbit divided by t rotation, whole thing squared. Okay. All right, now let's plug in the numbers. So AC rotation divided by AC orbit is equal to, plugging in the numbers, r rotation over r orbit. So here I need the radius of the Earth, that's the radius of the rotation, divided by the radius of the orbit, times the time for the orbit. So probably best to put these in the same units. So the time for the orbit is 365 days. And the time for the rotation is 1 day. I could put 24 hours, but then they wouldn't be in the same units. So these units cancel. You got to look up these numbers. The radius of the Earth, it's 6.4 times 10 to the 6 meters. And the Earth-Sun distance, you got to look that up. It's much bigger, 1.5 times 10 to the 11 meters. Sorry, I forgot a square here. Times 365 squared. The units all cancel, as they should, because this is a ratio. It's just going to be a pure number. 365 squared. So this is about 5.7. So that means that the acceleration that you feel from Earth's rotation around its axis is 5.7 times larger than the acceleration to the Earth's orbit around the Sun. Let's talk now about the more complicated case of non-uniform circular motion. So that's an object which is traveling in a circle, but not at a constant speed. So it could be speeding up or slowing down and moving in a circle. So you're going in a circle, I'll try to do it here, going in a circle and maybe you're speeding up as you're going in the circle, right? Or you're going in a circle and then you're slowing down but still traveling in the circle. Okay? In that case, if you think about it, there's 2 things going on with your velocity. You have a constant change of direction because you're traveling in the circle. That's what we call the centripetal acceleration. Sometimes it's called the radial acceleration because it's kind of in the direction of the radius. Then, in addition to that acceleration, you are also speeding up, right? So the speed up is the what we call the tangential acceleration. So if you think about it, both the magnitude of the velocity is changing, that's the tangential acceleration, where I'm speeding up or slowing down. And the direction of the velocity is changing as well, that's because of the circular path. So you have two pieces to your change of velocity. You're changing the magnitude and you're changing the direction. The change of the magnitude of the velocity, or the change in the speed, is what's called tangential acceleration. And the change of the velocity because of the circular path is what we call centripetal acceleration. Why is it called tangential acceleration? Because it's going to be parallel to the velocity, which is tangent to the circle. So if that object, what's shown here, the acceleration, part of the acceleration is in the direction of the velocity, so this object is speeding up here. Remember that something is speeding up if the acceleration is in the direction of the velocity. But it's also traveling in a circle, which is why I have this piece of the acceleration, which is called the radial or the centripetal acceleration. So you have both of those things going on at once. It's a more complicated problem now. If you want to get the total acceleration, you have to add those two. And those two are vectors. So one acceleration pointing towards the center, one pointing at 90 degrees to that, tangential to the circle. And so I have to add those two vectors. I can do it by eye. Using my parallelogram rule, my total acceleration would be pointing up this way by adding those two things tip to tail, like that. Okay. Maybe sometimes it's called a total, but otherwise just a, right? That's just the acceleration. It has two pieces, radial and tangential, but all in all, the acceleration points in that direction of that green arrow in this case. Here's another way to visualize it. This comes from a different book, which might help. Suppose I'm going in this path. Now, this is not a circular path, but let's not worry about that for a second. At this moment, the object has some velocity like this, and let's say it has some acceleration pointing down like that. Okay? And you can see that that orange vector, that acceleration, is the same in both of these pictures, the left one and the right one. You can break this vector A into x and y components, which is what's shown here on the right. So there's the x and the y component. That's what we're used to breaking it into, just by picking my coordinate system x and y like that. But there's another way I could break that into components. I could break it into a piece which is parallel to the velocity and a piece which is perpendicular to the velocity. So what I've done on the right-hand side is I'm choosing a coordinate system which is kind of like parallel to the velocity and perpendicular to the velocity. And then you can see like the component of the acceleration, like in other words, imagine casting a shadow of this vector onto the axis which is parallel with the velocity. That gives me my parallel component of my acceleration. And that's the one that's associated with the change in speed. That's what we call the tangential acceleration. And then there's a component of the acceleration which is perpendicular to the velocity. That's what we call the radial or the centripetal acceleration. So this would be the centripetal acceleration or the radial acceleration. Okay. So that's just another way of visualizing that. All right, so here's another clicker question. A car is slowing down as it drives over a circular hill. So here is the hill here. The car is going over the circular path, but also slowing down at the same time. So you can see that there's a vector here and a vector here for my initial velocity and my final velocity. Which vector describes the total acceleration of the car at the top of the hill? So A, B, C, D, or E. Go ahead and pause the video. See if you can wager your best guess for this one. Hopefully you have chosen your answer now. You have an idea of which direction that acceleration points. Common mistake is that students often will say D. So D would be correct if it was moving at a constant speed, but this is moving at the speed is changing and it's moving in a circular path. So you can see that d is kind of like the direction of the centripetal acceleration. That would be towards the center of the circle. But the object is slowing down, so it also has a tangential component to its acceleration. And so you add those two things together and you get the total acceleration. So the answer to this one would be C. You can also see it like this. If you just took those two vectors, like so put v1 is like this, and v2 is like, let's see, kind of like this, shorter, if I did it right. What's the direction of the change in the velocity? The change in the velocity goes from one end to the other, like this. So this is delta v. And remember, the change in the velocity, the direction of that, is the same as the direction of the acceleration. You still get an answer which points down and to the left, which is choice C. Okay, like I mentioned, we've got the tangential acceleration and the radial acceleration. One points tangent to the circle, one points towards the center. And suppose you want to get the total acceleration, or just the magnitude of the acceleration, I can treat those just like two vector components. Those are perpendicular to each other. So I can use my usual Pythagorean theorem here, right? This is the normal, this is a right triangle. I can do a right triangle just on this triangle here. And so the magnitude of the hypotenuse, which is the green arrow, is the square root of AR squared plus AT squared, radial squared plus tangential squared. Or radial and centripetal, I like to use those interchangeably. So the tangential acceleration squared plus the centripetal acceleration squared. That's the total acceleration. Last example here is a very tricky one, non-uniform circular motion. So let's do this example. Here it is. A ball swings counterclockwise in a vertical circle at the end of a rope, 2 meters long. When the ball is 30 degrees past the lowest point on its way up, its total acceleration is given by this. Determine the speed of the ball at that instant. Okay, so first thing to do is to draw a very careful sketch. So there's my sketch of the circular path. The object is at this point here, which is 30 degrees past the lowest point. So I'm choosing my angle theta, and that's going to be 30 degrees. And at that point, it has an acceleration which has a negative x component and a positive y component. And those two are approximately equal. I mean, the negative x component is a little bigger. I'm using this coordinate system here, plus x, plus y this way, plus x this way. Okay, so that's what it looks like. Now, let me redraw this again with a little bit sort of zooming in on that vector. So I just redrew the vector A there, kind of zooming in on it, just made it a little bigger to make my drawing easier to read. Now let me throw some xy axes in here. So there we go. And then hopefully you can see that this angle here is the same angle, that's theta. Now what we have in the information given in the problem is we have the x and y components of the acceleration. So I've got ax here and ay here. So we have those given there. What we would like to know is the centripetal and the radial acceleration. So this dashed line here is the radius that goes towards the center of the circle. That's the same as this line here. Okay. So what I want to do is break the vector A into components which are parallel to the radius and perpendicular. And to do that, I need to cast the shadow of the acceleration onto that line there. So this one here is the one that's perpendicular to the radius. This is the one which we would call AT, tangential acceleration. And then this line here would be the centripetal acceleration, AC. Okay. All right. Let me call this angle phi, and let me call this angle something else. Let me call it alpha. And we know this angle here is theta. Okay. Phi we know. So you can easily figure out phi given this information. Okay. And furthermore, I know that phi plus alpha plus theta is 90 degrees. So that can give me alpha. So I know for sure that phi plus theta plus alpha is 90 degrees, pretty clearly from that picture. Okay. So here's the plan. First thing is to find alpha. Well, I guess the first thing is to find phi. The second thing is to find alpha using this relationship here. Once I know alpha, I can then figure out the centripetal acceleration, find AC, and then I can use AC is equal to v squared over r to figure out v. So let's do it. Start on the next slide. So first step, find phi. That's just going to be trigonometry on this triangle here with the blue x and y components. Tangent phi is opposite over adjacent, ay over ax. So tangent of phi is equal to absolute value ay over ax. Okay. So phi is the inverse tangent of ay divided by ax. So that's the inverse tangent of ay is 20, ax is 22. I only put positive numbers in because I always deal with positive numbers when I do trigonometry. That's going to give me an angle which is between 0 and 90. And that's 42.27 degrees. Okay, so next step, find alpha. Well, that's easy, right? Because we said phi plus theta plus alpha was 90 degrees. So phi plus theta plus alpha is 90 degrees. So alpha is 90 degrees minus theta, which is 30 degrees, minus phi, which is 42.27 degrees. And that turns out to be 17.73 degrees. Next step. Find the centripetal acceleration. That I can do by looking at this red right triangle. So cosine of alpha is adjacent, which is AC, divided by the hypotenuse, which is A. So cosine of alpha is equal to AC divided by the magnitude A. So AC is equal to A times the cosine of alpha. I could put numbers in here, but I'm just going to wait because I want to put numbers in at the very end. Finally, I'm going to use AC as v squared over r. So let's plug that in here. V squared over r is equal to the magnitude of A times the cosine of alpha. What am I trying to find? Determine the speed of the ball at that instant. So I'm trying to find v. So let's solve it for v. V is equal to the square root of r times the magnitude A times the cosine of alpha. Now let's plug in the numbers. V is equal to square root, r is 2 meters. The magnitude of A, got to be a little bit careful, so I got to use square root of ax squared plus ay squared. So I'm going to have 22 meters per second squared plus 20 meters per second squared. Whole thing square rooted, so I'm doing, that's the Pythagorean theorem, finding the magnitude of A, times the cosine of alpha, which is 17.73 degrees. That whole thing under the square root. Okay. Let's check the units. Sorry, and I screwed up these units actually. Meters per second squared, meters per second squared. So what are the units here? The units of V? Well, under here I've got a meter there, and then I've got meters per second squared, whole thing squared, but then under a square root. So I'm going to have meters per second squared, and that's it. That's meters squared per second squared. Under a square root, that's meters per second. So the units are good. And finally, when I plug the numbers in, I got 7.53 meters per second. So that's a very tough one. That's a very tricky problem involving non-uniform circular motion. Okay, so let me just take a moment to summarize. We've talked a bit about circular motion and uniform circular motion. That's when an object is traveling at a constant speed, uniform circular motion. We had a relationship between the speed of the object, its radius, and its period, which was 2 pi r divided by t. That's just total distance divided by the total time around once. The frequency was 1 over the period, and the angular frequency, or the angular velocity, was 2 pi times f. So you can also put a couple more equalities in there. The most difficult part is realizing that an object can be moving in a circle and be speeding up or slowing down, and that means it has tangential and radial acceleration. So again, if the object's speed is changing, it has tangential acceleration, and then the direction change, which is because of the circular motion, is called centripetal acceleration. And we solved a problem involving both of those as thinking of the centripetal and the radial acceleration as components of a vector. So your total acceleration, or your instantaneous acceleration, is the Pythagorean theorem, or the Pythagorean sum of the tangential acceleration plus the centripetal acceleration. So I hope that you have found this lecture useful, and will find it useful in solving some of those WebAssign problems. And thanks again for your time.